The tornado of dust could easily disable his equipment. On Mars, this would leave an astronaut helpless.
Ho, ho!
Like the first astronauts on the moon, Wes will make a live transmission.
Wow. Is that big? Is that stable? My goodness. Ground is soft. Beneath my feet, I can't see my feet anymore. There is a great deal of dust swirling around me. I'd pick up sand grains and feel them, see how those sand grains interact with the Martian atmosphere, picking up some of the sand and watching it go through my fingers, maybe tossing some up in the air just to see how far it's going to go. And this is a device.
First contact, and Wes is still able to stand upright and function normally. He tries an electronic wind measurement.
And there's a pretty good gust in through
But
there.
things are about to change.
650, 60 miles an hour pretty easily. Perhaps the winds are now strong enough that I can start to feel the torque on my arm and on the backpack. Looks like I'm in charge of static electricity. I can feel it in both hands. My goodness.
Static is building in the blizzard of fast-moving particles. The dust is sticking to his visor and instruments.
Yeah, they're pretty close to zero. Vibrating around, rotating around. I can hardly see now. I can hardly see.
After just 10 minutes, the sand, dust, and static electricity take their toll. Wes is working blind. His visibility is gone. His wind gauge and a helmet camera have both failed.
Power's on.
This activity, this experiment, is just one of a number of small steps that we'll take that I hope the crews that get to Mars find exceptionally useful, teaching the astronauts what could happen to them and what they should be looking for. The thing that really surprised me was the encounter with static electricity. And actually became a little bit concerned about it. Would that mean that, for instance, I was picking up a charge and all the instruments, and if I came in contact with anybody else, would I give them something they weren't quite prepared for?
In the freezing, airless deserts of Mars, spacesuit malfunction would mean certain death. Wes's discovery is a vital step on the road to the Red Planet.
So for me, and for everybody that I worked with, this was really new information. No one had really expected all of these things. So this will go in the ledger as the first set of observations of this kind.
The first actual footstep on the surface of Mars may be only a generation away. But for now, only Wes Ward has had a taste of weather on a Martian scale. And only he can imagine a dust storm that grows from nothing to cast its shadow over an entire planet. His vision of the Earth as a desert world becomes reality.
Now we have dust storms on Earth too, but because of vegetation and water, the wind is really held in check. Let's imagine that the Earth is a little different now. Perhaps we don't have any vegetation. Perhaps we don't have any water. Let's take one of those Martian-sized dust storms and bring it right down to home. A Mars day is just about the same length as an Earth day. And about 2 o'clock in the afternoon, when the sun has been beating down all morning, the ground is as hot as it's going to get that day. That's the time for Martian dust storms to spring up. A Martian dust storm might begin very simply. Maybe it's just a dust devil or two somewhere around the house. We might see a dust devil in the order of a few feet high, start to grow, spins a little bit faster and faster. On Earth, dust devils are really something of an amusement. But on a planet like Mars, dust devils are perhaps the dominant destructive force. Other dust devils come around, perhaps they're starting to coalesce. And what they are doing are starting to build into one giant dust storm. They're now growing up to the size of the house and maybe the trees. These are the first guard, the first wave of a big and deadly storm coming.
Dust devils are filling the air around the house. But this is no hiding place. Martian dust is as fine as talcum powder. It will creep into the house through any gap it can find. And it will soon be impossible to breathe. Dust devils stretch to the horizon in every direction. The approaching wind will sweep up the dust, creating a wave 5 miles high, sandblasting everything in its path. The storm is now moving at well over 100 miles an hour, and there is nowhere to run.
Oh, I don't like this.
This is just the beginning. A dust storm on a Martian scale would grow to cover the Earth. Humans will face these monstrous storms when Wes Ward's dream is realized, and astronauts travel to Mars. But the dust storms that roam the deserts of the Earth are held in check by our thick atmosphere, and 2/3 of our planet is covered by ocean. The Earth will never turn to dust. But there is another storm, far more violent than anything that can be found on our near neighbors in the solar system, weather far more extreme than the Earth's, or the mighty dust storms of Mars. The outer solar system, realm of the giant gas planets, is the true home of the superstorm. The planet Jupiter is so vast that more than 1,000 Earths could fit easily inside, a planet that's all atmosphere. As long ago as the 17th century, the astronomer Cassini saw a mysterious dark shape moving on Jupiter's surface. The Great Red Spot turned out to be a type of hurricane, twice the size of the Earth. Now, after more than 300 years, the Great Red Spot is still raging, and it's not alone. The surface of Jupiter is teeming with storms. Weather on Earth is powered by the sun's heat, but Jupiter only gets a fraction of this energy because it is 5 times further from the sun than we are. Jupiter's weather is driven by a powerful engine deep in its secret interior. The greatest flashes of lightning ever seen were detected on Jupiter by the Galileo spacecraft. Thunderbolts 50 miles across and 100 times brighter than typical lightning flashes on Earth. Only Jupiter's outer surface is visible, but its lightning gave us a window into the planet's hidden interior. And when 700 miles of cloud broke its surface, planetary scientists were seeing the same thunderstorms as those on Earth, but on a terrifying scale.
And this was extremely exciting because now we had lightning on another planet, and we've actually correlated the lightning with certain types of clouds that you see on Jupiter. In particular, these beautiful bright white plumes that come out of nowhere and just erupt in the low pressure regions on Jupiter.
Jupiter gives out twice as much energy as it receives from the sun, with heat left over from the planet's formation. As it cools, hot gases rise towards the surface, powering thunderstorms as they go. These are the thunderstorms on Earth, seen from space. Tim Dowling wants to know what Jupiter's thunderstorms look like from the inside, but he only has sparks of light to guide him.
Of course, when we do planetary science, we're always looking down, and when you're a terrestrial meteorologist, you get to look up where you actually get to fly through. We have a lot of limitations. We have this great existence of lightning. We know some other things about it, but we can't get inside the thunderstorm on Jupiter, and that is killing us.
Tim is a professor at the University of Louisville. For the past 5 years, he's been analyzing data from the only spacecraft to attempt the perilous descent through Jupiter's atmosphere.
3, 2, 1. We have ignition and liftoff of Atlantis and the Galileo spacecraft bound for Jupiter.
In 1989, Galileo was launched on a mission to study Jupiter and its moons. After a 6-year odyssey, it was in a position to drop a probe through Jupiter's clouds.
We were able, because it was an orbiter instead of a flyby mission, to plan very carefully a sequence of experiments or observations where we could look for lightning, and we knew pretty much where to look. We want to look in the low pressure rather than high pressure, in the low pressure zones on Jupiter.
Low pressure means thunderstorms, and the probe went in at 106,000 miles an hour. The probe headed for the center of the planet. It fell for 57 minutes, but to Tim Dowling's dismay, it detected almost no water. And with no water, there was no sign of thunderstorms. By sheer bad luck, it had hit one of the driest regions on the planet. 97 miles down, radio contact with Galileo was lost, and the probe was gone forever.
Just one sample of this enormous planet, it's tantalizing, but it raises more questions than it answers.
Tim hadn't found his thunderstorms on Jupiter, so his quest to understand them shifted to the Earth.
We're here inside the atmosphere of Earth, of course, and looking up. So you can get a great deal of information about the storms, the mechanisms for thunderstorms and lightning by doing very careful measurements of Earth's atmosphere and then try to carry that over to Jupiter.
Those measurements are about to be made. At the height of the summer storm season, Over 100 weather scientists have converged on the Kansas prairies for the biggest study of thunderstorms ever held. They're hunting for supercells, the most dangerous thunderstorms on Earth. Planetary scientists like Tim Dowling believe that giant versions of these storms are producing the lightning flashes beneath Jupiter's surface. The hot afternoon sun is evaporating moisture from the land, creating tall columns of rising cloud. Thunderstorms in the making.
And I'm sort of thinking that you guys might want to head down that way.
The Earth experts want to understand how storms build. In order to predict them, they need a three-dimensional portrait of a storm. But they have to catch one first, and they have a Jupiter expert on their tail.
They've got storms here, 10 o'clock, 2 o'clock, all the way across the horizon, and they're gonna have to make some choices. It's gonna be really cool to see how they decide where to go to put the first balloon up.
Command Post radar shows that one of the storms they're tracking could become a supercell. Ground teams race to head off the moving target, and Command brings out its secret weapon. The heavily armored T-28 military aircraft is scrambled to fly directly into the heart of the storm. Its mission is to measure the strength of lightning inside the supercell, something that can only be done from the air. It sounds like madness, but this is the only aircraft in the world that's licensed to do it. Tim Dowling hopes that by establishing a relationship between lightning intensity and the size and growth rate of the Kansas storm, he'll be able to do the same for Jupiter.
What we need is a fairly robust or very good model of lightning and thunder. If you have a model that does a good job of predicting or describing Earth's weather and Jupiter's weather at the same time, then you feel much more confident about the underlying physics and your understanding.
Ground forces launch a balloon into the storm to measure how fast and how high the thundercloud is rising. Above them, the T-28 approaches the most dangerous part of its mission. The massive updrafts of the storm threaten to tear the plane's wings off in a process known as wind shear. The same forces create lightning when water droplets freeze into ice particles at high altitudes. As they rise inside the storm cloud, they rub against each other, creating massive charges of static electricity. Eventually, enough charge builds up to explode as lightning.
And it's getting pretty dark. I don't know what's coming next. And lightning. Very close. Lightning, lightning. Lightning, lightning.
The thunderstorm is now 10 miles high, the maximum possible before it hits turbulence in the atmosphere and flattens out. This is an enormous storm. Suddenly, a tornado touches down on the horizon, the supercell's frightening calling card. The second balloon launch has to be fast. Just a few miles away, the twister is already causing havoc. And now it's heading their way. The T-28 has detected so-called super bolts in today's storm. On hot summer days, the atmosphere expands, and thunderstorms can climb much higher than normal. This one went to a height of 10 miles, with updrafts of 100 miles an hour. Tim Dowling has seen that the more room a thunderstorm has, and the faster it grows, the bigger the lightning it produces. And in his imagination, he descends into the colossal thunderstorms to the west of the Great Red Spot.
See this incredible eruption, almost an atom bomb that's going off. And it's the size of Alaska, this thing. So it's just going to be like a wall, an enormous wall that goes up. And instead of going up 10 miles or so, we're talking 30 miles and just towering up overhead.
Now Tim wants to compare Jupiter's lightning with Earth's. No one knows lightning like a T-28 pilot.
This thing can get hit by lightning.
Yes, in fact, we've...
Charlie Summers
got over
shows him the
20
damage.
lightning strikes that have hit the aircraft.
What does that look like? Can we see?
Yeah, let's take a look back here. Usually the lightning, when it strikes the aircraft, doesn't leave any damage, but usually we get an exit. Like,
oh, interesting.
This is an exit where the lightning actually came out. Now, it's not that even when it happens, but I usually smooth them out a little bit just...
So that's like a thumb's width, that's a typical size?
Yeah, and that's a pretty heavy lightning bolt that is burned as it comes out. And the aircraft's been hit...
Oh yeah, there's chips all down here.
Yeah, and then there's bigger ones here.
The average commercial airliner is hit by lightning once every year. There's no armor plating like a T-28, but they're designed to take 10 times the jolt packed by a typical thunderbolt on Earth. But could they withstand a thunderstorm on the planet Jupiter? And lightning bolts that deliver the electric power of a large industrial city in a single heavyweight punch.
One thing, of course, I'll never get to do is fly in an airplane through Jupiter's cloud, but I would just love to look out the window, just like you do flying in the window seat of any airplane. And the question is, what would it be like if you were actually there?
Let me just put that up for you. There you go.
Ladies and gentlemen, for those of you who are awake, there's some pretty spectacular storm activity out on the right-hand side of the plane. Although it's some distance from us, we could be experiencing some turbulence ahead, so I'm going to go ahead and put the seatbelt sign on for a while.
If you actually flew in the vicinity of one of these enormous thunderstorms, you might see more than you want to see. If you actually go up to the cockpit, then you can get this incredible panorama of what's above, below, and to the side of you.
Alpha,
The scope is so huge, it would fill your peripheral vision, and you might wonder what the heck you're doing there. Of course, if you're looking at a tiger behind bars, it's a beautiful, magnificent animal, but if you actually climb into the cage, that's a very stupid thing to do. The actual energy that's contained in one of these enormous discharges, lightning strokes on Jupiter, is over 100 times more than the typical lightning stroke on Earth.
But lightning isn't the only problem. On Jupiter, the updrafts reach 200 miles an hour, twice as fast as the biggest thunderstorms on Earth. Jovian thunderstorms are driven by enormous energy, boiling up from the center of the planet. A superbolt on Earth causes a pinprick in the T-28. But Jupiter's lightning could blast a hole in the fuselage.
Although it might be a great honor to be on Jovian Airlines 101, it would also be probably your last flight on Jupiter.
But these nightmare thunderstorms are small fry, providing energy for something far more terrifying. Energy to feed a storm twice the size of the Earth. Energy that's kept it churning for more than 300 years. Energy that powers the Great Red Spot. Jupiter's Great Red Spot may have been around since long before the dawn of astronomy, and it looks like it will exist forever. But how can it live so long